recording. Come on. Okay, welcome to the second last lesson of the year. So sad. Okay. Oh no, what am I doing? I just printed on something. Okay, so this is 3.3, non-linear regression. The first 2 days of this chapter were about linear regressions and correlations, but in the real world there's a lot of non-linear relationships. For the people that took functions, you know that. There's a lot of real world applications that are not linear. So let's delve into this. It's going to be a short one. I'm going to predict 22 minutes. All right, here we go. All right, so many relationships between two variables are not linear. Linear, of course, is y equals mx plus b. The most common non-linear relationships are, give me an example of a very common, let me get rid of this thing. How do I erase? Is this erase? Oh, there we go. Okay, how do I get rid of this now? Oh no! No, stop! Okay. I don't know what's going on. Anyway, you guys see that okay? Everyone still there? Anyone?
Hi, sir.
Okay. So, give me an whoever that was. Krishna, can you give me a non-linear relationship that's very common in the real world?
The real world. Quadratic.
Quadratic. I would say that's probably way up there. And the equation is not y equals mx plus b. It's y equals... Anybody? Of course, ax squared plus bx plus c in general case. And it kind of looks like that. Or what else can it look like? Like that. All right. If you have a negative a value, it goes down. Okay, give me another one. Okay, very silent today. I'm going to suggest a cubic. You guys have taken advanced functions. You've learned about cubics. So how is it different from a quadratic? All right, well, there's an extra term, right? So you have a cubic term. So instead of ax squared, it's ax cubed. And then you have a squared term, bx squared, plus an x term, cx plus d. And what does that look like? I know you've all, most of you have taken functions, so tell me what a cubic looks like. If it starts in the left bottom quadrant, it would go up, and then what happens?
It goes down for a bit and then back up.
Yeah, it could go down. It could level off and go back up, or it could actually go down and go back up. Or if you have a negative coefficient, it could be the other way around. It could be, something like that. All right, and another common one is exponential. It happens a lot. And general equation. Someone want to give me the general equation? Oh, you guys are very shy today. Very shy. All right, let's go with y equals ab to the x. You could have a c, but generally speaking, I don't know why the regressions don't have the c in it. It could be a constant, just like we have a constant here and here, but when you do the regression, for some reason, it doesn't include the c, so we'll just leave it off. And it looks like, what does an exponential function look like? Well, there's an asymptote, typically a horizontal asymptote, and it gets steeper and steeper. Or it could be the other way around. It could be going towards the horizontal asymptote. Okay, we're good. So when we model things with non-linear models, we're not going to do it manually. It's way too complicated. The last 2 days, we did linear regressions manually yesterday with a formula, complicated formula. The formula is going to be more complicated for non-linear, so we're not going to do it manually. So we're going to use a graphing calculator or a spreadsheet, and again, these are the most common ones. Our tool is going to be the coefficient of determination, which is the r squared value. We talked about that before. It's always a value between 0 and 1. A 1 means this is the perfect model. Every single data point lies on this curve, and model of 0, well, you're not going to get 0, but anything close to 0 is going to be a very, very poor fit. All right, so how do you find the best curve? Generally speaking, the curve of best fit is the one that has the blank r squared value. Everyone, give me the word. Everyone. Okay. Wow, you guys are. Where's Krishna? Where's my go-to girl? Krishna, you there? Wow. Highest r squared value. You guys are still there.
Yeah, I'm so sorry. I was just talking to my mom.
No problem. Yeah. All right. No problem. So generally speaking, the one with the highest r squared value is the best one. However, a lot of times you'll have models that are competing. They will be very, very close with the r squared value. So the best model may not have the highest r squared value, but gives blank results when blanking to initial or final state. So I'll just fill in the blanks for you. It has to give realistic results when you are extrapolating. So basically the r squared value, the one with the highest r squared value, is going to give you the best model for interpolating. But when you're extrapolating, you have to be a little more careful. Okay, so all right. Also, for the people that took functions, you can, if you have a lot of data points, you can make a curve going through all the data points if you have a higher order polynomial function. If you go higher than cubic, you could go to quartic, quintic, what's the next one? Sextic or septic or octic or whatever polynomial functions, you'll get very complicated functions that go up and down and all that. However, mathematically, it's probably not logical that something that complicated represents it. So typically higher order polynomial functions are not logical. They're just they're convenient because they're accurate. They for interpolating, most of the points are really close, but that probably doesn't model the actual science behind the relationship. So just be careful about that. So let's look at an example. I just dropped my pen, sorry. And I don't know where it is. Oh, here it is. Okay. So here's some data. The following, a laboratory technician monitors the growth of bacterial culture and collects the following data. So at 1 hour, there was 10 bacteria, 2 hours, 21, blah, 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 blah. Okay, so we go up from 1 to 14 hours. Here's a scatter plot of that data. In Excel, what I just did over the last hour or so, I've plotted, and this is very easy to do. If you have a spreadsheet, this takes and you guys did it with that initial correlation assignment. But if you do a line of best fit, trend line, you get an equation and an r squared value. If you do a quadratic, you get a different equation, you get a different r squared value. And again, none of these does the model go through all the points. The cubic, again, the r squared value is a little higher. It's a little smaller. It's in 0.9947. Exponential looks not too bad initially, but then it starts to go off the rails here at high values. And hopefully we're able to print this last one. Were you able to print this last one? Power. What is a power function? A power is x to an exponent. The variable isn't the exponent, but the exponent could be just a number. So this is not quite quadratic. Quadratic would be exactly 2, but this is 2.08. So this is considered a power function. Okay, so very easily, what's the best one? What's the best model? The best model is the one with, generally speaking, highest r squared value. Which one is it out of the ones I just showed?
The quadratic one?
No, I don't think so. Quadratic was 0.988, and this is 0.9947. So, generally speaking, the one we'll just out of the one shown. Oh, sorry, model done. Okay, so it's cubic is the value is 0.9947, but it's the cubic model. However, if you're going to use this model, you want to make it accurate for extrapolating too. So let's do some extrapolations. Okay, so let's do it at time t equals 0 and time t equals 20. What does each model predict? So let's just write down the equations from the previous page. That was the linear one, 114x minus 281. The quadratic was y equals 3.98 x squared plus 54.7x minus 122.2. The next one was y equals, this is the most complicated one, minus 0.72 x cubed plus 20.1 x squared minus 45.6 plus 24. Exponential was y equals 17.7, 1.44 to the x, and the power was y equals 6.5 x to the 2.0803. All right. You don't even need calculators for the t equals 0. You can do all of these in your head. So for the first one, t equals 0, what would be the linear prediction? So you're putting x equals 0. Actually, these should be t's, not x's, but yeah. So if t is 0, 114 times 0 minus 281 is just minus 281. It's just going to be the constant, right? So this is going to be minus 122.2. This is just going to be the constant 24. What is this? We should put in x equals 0. I'm not going to move on until I get somebody to answer. Oh, come on, guys! If you can handle calculus and functions, you can handle this question. If x equals 0, what is y? What's 1.4 to the 0? What's happening, guys? You guys are so quiet. Okay, anything to the 0 is 1. So this is just 1. So 1 times 17.7 is 17.7. What about this one? What would this be? If x is 0, well, 0 to anything, to any power is 0. So this is just going to be 0. All right. Extrapolating at t equals 0. You guys were just wanting me to give you the numbers? I take that as a yes. So if you put in x is 20 here, you're going to get 1999. Here you're going to get, if you put x is 20, you're going to get 2,564. Here you're getting 1392. Here you're going to get, if x is 20, you're going to get a much bigger number, 26015. And here you're going to get 3,307. Again, our highest number at 14 hours was 1410. It looks like it was going up. So you would expect it to be, I don't know what you would expect, but yeah, it looks like some of these are a little higher and some of these are a little lower than what you would expect, right? All right. I'm focusing on the cubic model because we said that was the best one. What does the cubic model predict when t is 1 hour? I'm just going to do one more prediction here. So if t equals 1 hour, it's going to be, we're going to plug in t is 1, so it's going to be minus 0.72 times 1 cubed times 20.1 times 1 squared minus 45.6. Ooh, forgot the x here. 45.6 times 1 plus 24. So if you do that, you get minus 2.2. So that's kind of a funny result. So we know it's not minus 2.2 because at t equals 1 hour, it was 10. So none of these models are going to be perfect. Like they all have flaws. So we just want to choose kind of like the best one that we can use for interpolating and the best ones we can use for extrapolating. Can we go to the last page? I told you this was going to be quick. Where's the last page? Hold on here. I don't have the last page printed. Oh, here we go. Conclusions. So what are we going to conclude? So, in general, let's look at what we did initially. We have to be careful when we extrapolate, but when the curve of best fit is the one that has the highest R-squared value, and this is generally speaking for interpolating. Why don't we add that to the first page? Okay. So, which one was the best model? I'm just going to show you instead of writing right in front of you, I'll just uncover. So, the best model for interpolating is the cubic model, since it has the highest R-squared value. Some caveats though, right? All of a sudden that got a lot dimmer. Oh, there we go. Some caveats. When we extrapolate, it's not quite the best. Why not? It isn't accurate for extrapolating between 0 to 2 hours because it shows a decrease from initially, it showed it starting at 24, and then it goes down to actually slightly negative numbers, and then it pops back up. So even though it had the highest R-squared value, it wasn't that good for the first hour. So we have to make a little note about how the little problems on the initial values. It isn't accurate for extrapolating between 0 to 2 hours because it shows a decrease from 24 to less than 0 and then increasing again. Another problem is on the high side. On the high side, at 20 hours, it's at 1392, which is even less than what we had at 14 hours. Where is it? At 14 hours, we're at 1410. So it looks like it's going up, but the cubic model predicts that it's actually going to start leveling off, and even after 20 hours, it's actually going to go down again. So that's not the trend that we see here. So after 20 hours, the cubic model, the curve starts to level off and then decrease. So what might be a better model than the cubic model? If you're going to pick for the high values, which one would you pick? Which one is best for this area up here? Like for this the cubic model is going to predict that it's going to go down, right? So which one of these four would be the best ones? Best one for future progress. It's hard to say, but I'm thinking maybe the linear one is best. This is pretty much a straight line here, so I'm thinking at the high end maybe a linear model would be better. I'm just eyeballing it, right? So I put that in my notes. So after 20 hours, the curve starts to level off and decrease. It might make more sense to use the linear model to extrapolate past 14 hours. So, in general, I don't know if you guys are copying this or not, but or you can just wait and print out the completed page. But this is true for every single case. In general, use the model with the highest R-squared value for interpolating, but use caution and logic when choosing a model for extrapolation. Okay, you have to kind of look at what is reasonable, what's realistic. Can my values be negative? So it doesn't make sense. So this is a hard and fast rule. So that's interpolating. Just go with the highest R-squared value. All right. Lastly, use the line curve of best fit to predict the population at 6.5 hours. Again, this is in 6.5 hours is an interpolation. So if we're interpolating, we just use the highest R-squared value, which is the cubic. We just punch it in, get our equation, sub in 6.5 hours, and if you look at what are we expecting? Between 6 and 7, we're expecting a number between 320 and 475. So I don't know, what would you expect? 370, 380, 390, somewhere in there, And if you do the model, you end up at 381, and that seems reasonable. So we can use the model with the highest R-squared value for interpolating, but just be careful if you are, when you're extrapolating, then you really have to, do it on a case-by-case basis and think logically. And that's it. That's the whole lesson. So I'm going to stop recording, and then we'll, where is it? 20 minutes. Look at that.